Yes, so how does this work? Pointer, laser pointer, all set. Okay, so hi, we talk in English, right? You will hear me speaking in Hebrew in semester bet for Mishvaot Differentialiot. So enjoy my talk in English as long as you can. So my name is Ronny Bartsch, and I'm working on application of physics or statistical physics to physiology. And I'm mostly interested in movement disorders, so how people move, so to say, and also sleep. And today I want to tell you a little bit about recent findings in my group on sleep regulation, and in particular this topic of interacting networks in the brain. So you have in the brain sleep and wake promoting neurons and how they interact to trigger arousals and sleep stage transitions. So we go into these details in the next couple of slides. So don't be afraid if you don't understand so much from this title right now. If you have any questions during the talk, just shoot, okay? Don't be shy, just ask me. Good, so this is work done in collaboration with people in the physics department, Shlomo Havlin and Hila Dvir and Lior Appelbaum, who is located in the Nano building. He has in the uppermost floor of the Nano building all his fish, his zebra fish aquariums, and I worked with him and also with Plamen Ivanov from Boston and Harvard Medical School. Okay, so how do we measure sleep? How do we perform experiments on sleeping people? And for this, we need to get a little bit a background. And the most important tool to measure sleep is the EEG, the electroencephalogram. You have to move this to the side because it hides the title, right? So electroencephalography, these are basically brain waves. This is the activity that you measure from your brain. So there are electrodes put on the skin of your head, of your skull, and you measure with a high resolution the electrical activity of your neurons, so to say, or of a group of neurons. And very interesting fact is that the EEG was kind of developed by Hans Berger. This was a German neurologist, and he came to studying EEG or inventing the EEG by a rather tragic accident. So what happened to him was that after school he served in the German army, and he had there an accident where he fell with his horse down a hill, and he almost got killed by what was at this time a kind of a tank, so to say. It just stopped right before him before it crushed his head. And this accident happened in Würzburg in Germany. And a couple of hours later, he received a telegram. So at this time, they didn't have email or a phone. So he received a telegram from his parents, who were located in Coburg, which is 150 kilometers away from Würzburg. And they asked him if he is doing all right. And he was puzzled by this. How could they know that he had an accident? I mean, news didn't travel so fast at this time. And later he learned from his sister, with whom he was very close, that she had at this day, at about the time of the accident, a bad feeling that something had happened to him. Okay, so we call it telepathia today, but Berger didn't have an explanation for this, and he kind of spent the rest of his life to try to explain this phenomenon that people far away can kind of sense that something happened to their loved ones. And he kind of hypothesized that his brain in this time of the accident sent out some wave, sent out some signal that his sister received and then sent him the telegram, so to say. So, and he started to experiment with putting electrodes on the brain and discovered the EEG, discovered the electrical activity of the brain. And the first thing he saw, so this was an experiment he did in 1924, almost 100 years ago. And the paper was only published 5 years later in 29. But what he observed is this kind of alpha wave. Okay, so it's called also Berger's wave. So you see this kind of periodic signal, this wave that you measure predominantly in the back of your skull, especially when you close your eyes. So when you close your eyes, you see immediately in the EEG that brain alpha waves increase. So here you have as a reference signal a 10 hertz wave. So you see this is slightly faster. And regarding the voltage of the EEG, it's about 100 times lower than the ECG. What you measure your heart activity is in the order of volt, right? And here the EEG is in the order of microvolt, 100 microvolt. And relative, relevant frequency bands are in the order of from 0.5 to 4 hertz, which are called delta waves. Talk about this in a minute, or up to 100 hertz. These are gamma waves that you predominantly find in people who have an epileptic seizure. Okay, then you have very fast gamma waves. So the EEG was developed, but it roughly took 30 years until those guys decided to put it on people in the sleep lab. Okay, so I don't know how they studied sleep at this time without an EEG, but only in the 50s, in the 1950s, this guy Aserinsky, who was a PhD student of Nathaniel Kleitman, he decided to just put an EEG on people in the sleep lab. And he discovered a lot, but he's most famous for the discovery of Rem sleep. So Rem sleep, as you know, is this sleep where we are dreaming. Okay, we are kind of dreaming about events or falling down from somewhere usually. So this is first discovered in the 1950s, and somebody notices something interesting on this slide. Any interesting observation? Nothing interesting? Oh. Already in the first slides, nothing interesting. When I see in presentations pictures like this of people and below the numbers from what year to which year they lived, I always start to calculate how many years when did they die, at which age, you know? So, and you see that this one became older than 100, right? 104 years. And indeed, this is a picture of him in 1995 at a sleep congress. He was 100 years old and he gave a talk on sleep and told people how important it is to know about sleep and also to sleep well and sleep enough. And so this was his fate. Aserinsky, as you see, he died in his 70s. He didn't have such, was not so lucky. He had actually a car accident next to his home in San Diego, and he fell asleep while driving. So both of their careers and also their ends were very much related to sleep. Okay, So let's talk a little bit about what you observe when you take an EEG from people sleeping. So there are different sleep stages, okay? So according to patterns that you see in the EEG waves, you can define different sleep stages. So there's foremost light sleep. So light sleep is characterized by these sleep spindles. These are short bursts, usually half a second long, 12 hertz, related to memory consolidation. So when you learn for a test in quantum mechanics and then you go to sleep, you should have a lot of these sleep spindles. The more sleep spindles you have, the better you will perform in the test, okay? So ask Ali Bakai to give you some medication to improve your sleep spindle activity during light sleep. Just kidding. And you also have K complexes, okay? This is another characteristicum of light sleep. Deep sleep is usually where our bodies mostly recover from daily activities. So if you do, when you run a marathon, for example, or you do some very strenuous physical activity, you will have more deep sleep in the following night. And deep sleep is characterized by these delta waves. You see these waves that look like a Greek delta, like the letter delta in the Greek alphabet. So these are delta waves, and they are very low frequency, just from 0.5 to 2 seconds duration, and they are very large. No? They have 75 to 100 microvolt. And another aspect of sleep, or another sleep stage, is REM sleep, as we just talked before. This is very much indistinguishable from wake. So if you just give me a EEG of a person that was in REM sleep, I cannot tell you whether he was awake or in REM sleep. Actually, it's very difficult to distinguish. But what is different to wake is that the EMG, the muscle activity, is zero during REM sleep. So this has the advantage that you don't act out your dreams, right? When you're running, that you don't hurt your boyfriend or girlfriend or husband and wife in the bed when you run in your dreams. So you're basically paralyzed during REM sleep. This is also the reason why sleepwalking does not happen during REM sleep, but more during non-REM sleep, during light and deep sleep. Also, what you see is during REM sleep is that your eyes have periodic movements, and this gave REM sleep actually its name because it's called a rapid eye movement sleep. Okay, so this is also something that you, when you observe your friend sleeping, what you would see when he or she is in REM sleep. Good. So when you look at sleep stages throughout the night, so you go to a textbook on sleep medicine, for example, you see a figure like this, where you have typically these kind of hypnograms, they are called, where you have here on the y-axis the sleep stage over time. Okay, so here this person went to sleep at 11 p.m. in the evening, woke up at 6 a.m. in the morning, and you have here the going to sleep stages. So first you have light sleep, then you go into deep sleep. You spend here about half an hour in deep sleep, then you go up in light sleep and into REM sleep. This is the green thing. And then after REM sleep, you repeat this cycle about 4 to 6 times throughout the night. And something interesting you observe here in this figure. I'm asking you all the time these questions to see that you are still here. So something interesting.
The red area gets smaller over time. That's when the body recuperates, right?
Yes, so you're right, Odelia. The red bar here gets smaller, whereas the green bar gets longer, right? So this is related to hormonal changes. So in the beginning, you have much more melatonin in your brain and less cortisol in your body, so you can reach these deep sleep stages, whereas towards the end of the night, your cortisol level increases, your stress hormone increases, so you have less deep sleep and more REM sleep. So this also shows you when you So this is usually your pattern throughout the night, plus minus. If you were running a marathon and you have a party afterwards and you go to sleep only at 2 a.m., you won't get enough deep sleep to recover, right? So this is also something you need to consider, because this kind of sleep cycle with a lot of deep sleep in the beginning and more REM sleep towards the end of the night, this is something that is constant in your circadian rhythm. Okay, so if you all the time used to go to sleep at 11 p.m., you wake up at 6 p.m., this is kind of your cycle. So if now on the weekend you first you do some strenuous activity and then you go to party and you go to sleep very late, you will miss out on these recovery periods and also on kind of memory consolidation. So just for you to know this. This is what you see in textbooks. Okay, this is the ideal world. However, in the sleep lab, when you look at people, you see a very similar pattern, but something in addition. So it does not look as clean as in the books. You see here a lot of these short awakenings. You see this? So you go to sleep, and this person had here some deep sleep, then went into REM sleep, again to light sleep, but all the time you have these short bursts of awakenings. You see this? So a lot. All of us have throughout the night about 10 to 15 of these short awakenings that we don't remember in the morning because they are just too short. And nobody knows why. Okay, this happens independent of age, independent whether you are sick or you're healthy. You have this short awakening. So it looks like this is something that is really typical for the brain. Okay, but nobody has an explanation for this. So the question is, can we learn something applying physics methods from statistical physics to analyze these data, to model these data, and perhaps to learn something about the mechanisms that underlie this. Good. So let's first do something that we all know. Let's do a statistics. Okay, a statistics of these kind of signals. Okay, so we have here a signal that is basically, you can simplify it to just wake durations and sleep durations. And let's just do a statistics of these signals. You take here on this plot, you take on the x-axis the duration of these arousals, of wake episodes. So these are the open symbols, and you just plot how many times you find 1 minute awakenings, how many times you find 1 minute and 20 seconds, how many times you find 2 minutes awakenings, and so on. And if you plot it, this is something very interesting. If you plot these statistics, this distribution now on a double logarithmic plot. So you see here, this is logarithmic and this is logarithmic, and you get here a straight line, okay, a straight line of this distribution. It means that the process you observe, the process you measured is a power law, okay? It's a power law. So this fitting line here is characterized by a distribution PD proportional, or that scales with the duration to an exponent alpha, minus alpha, okay? So this is alpha, this is the exponent. So you get a power law for wake durations. Now you plot also the sleep durations, okay? How long you were asleep in, your sleep bouts. You put your sleep bouts in this plot and you get the curve like this, okay? It's not a straight line, it looks curved. So the next idea you have, okay, instead of plotting it on a log-log plot, I plot it now on a log-lin plot. So I keep here the logarithmic axis, I put here a linear axis, and now I have here again a straight line. Okay, I have here a straight line. So if I have a straight line in a log-lin plot, this is an indication for an exponential law. Okay, exponential law, you know, from nuclear decay. This is an exponential law. So there are many examples in physics where we have an exponential decay. an exponential law. So, and for a exponential process, you obtain this time constant tau. Okay, what does this time constant tau tells you? Anyone? You learned about exponential processes, right? Nuclear physics.
No, we didn't.
No.
Yeah.
Ah, okay, but you know that you have half times, right, in nuclear decay. So, so basically, this tau here gives you the average of the process. So you have a mean decay time. So 22 means here that in average we are 22 minutes asleep before we wake up. Okay, before we have a short burst of arousal, a short burst of awakening. 22 minutes. So you can obtain such a value, a mean value for an exponential process for sleep, but you cannot do this when you have a power law. Okay, when you have a power law, you cannot, it doesn't make sense to ask what is your average wake time, arousal time. So what is the typical length of an arousal? Doesn't make sense because it's a power law process, and for the power law process, you cannot calculate a mean. But it makes sense to ask what is your average time of being asleep in one piece, okay, at one bout. And this is an exponential process, so you can calculate this by just doing a fit through these points, and you get 22 minutes. So 22 minutes is about the time you spent asleep in one time. So this also changes with age. You know, when you have elderly people, this is usually smaller. It also changes for different animals, as we will see in a second. So you can do the same statistics now for different animals. So humans, we just talked about. You can also take a cat. Okay, look at a cat. All these sleep-wake transitions. You can look at rats. Okay, so rats and mice, you see they have they are a lot asleep, and their awakenings are not so long like for us, you know. So they are constantly between sleeping and waking, and so for mice and rats you see something very, very similar. And you can do the same statistics. Okay, you can do again log-log plot for the arousals. So you see here, these are the mice. Okay, the triangles are the rats, the circles are the cats, and here the squares are humans. And you find within the arrow bar that it's a very similar slope. Okay, very similar slope. Somebody notices something interesting? No? I'm all the time asking you these questions, so מעצבן כבר. I mean, compare, last time we saw this slide was here, right? So here we have a very similar double logarithmic plot and the awakenings, and now here we have again double logarithmic plot and the awakenings. And what's the difference? Look at the alpha value. 1.3, 2.3. How come? Any idea? Okay, so very easy answer. This is an integral. Okay, this is an integral, as this is just a pure probability density function. So that's why you get a +1 when you do an integral. Okay, so good. But for the log-lean plots, you see, we have different results. So here we get the same, okay, for the arousals, but for the sleep durations, you get something very different for the different animals. Here we have the 22 minutes for the humans that we saw before, but cats have much shorter tau, and rats and mice even shorter. And this is because this is related to brain size. Okay, the longer, the bigger the brain usually is, the longer you can stay asleep without waking up every 5 to 6 minutes. Okay, so when you plot now the curve for an elephant, where would you see this? How would this look like for an elephant or for a blue? No, a whale is different. So let's stay with animals that live on land. So how would an elephant look like?
It will be above the cow.
It will be above, right. It will be above the human. It will be about here, okay? It will be about here because they have bigger brains, okay? They are not smarter typically, but they have bigger brains, so they can be asleep longer in one piece, okay? Good. So we learn about this coexistence. So we have a power law for arousal awakenings, and we have this exponential process for sleep bout durations. And the question is why, I mean, do we have any idea why this happens? Can we model this? Can we get any insight into this? So, and there is a model in statistical physics. It's called, or a framework that is called self-organized criticality. So what is self-organized criticality? Have you learned already a little bit on phase transitions in statistical physics?
No, it's on the semester, but
Yeah,
okay. So okay, but you know phase transitions, right? Phase transitions is when you go from, when you freeze water, the phase transition is from fluid to ice, for example, okay, or from fluid to steam. And typically, it's very difficult to keep a system at the critical point, okay? So you all the time have to manipulate the system, so you have to adjust the system that it is in criticality. However, a self-organized criticality system is pushing itself all the time in criticality. So, and this is nicely shown by this sand pile model. So when you go to the beach and you drop grains of sand on top of each other, you build some little mountain, right? And if you cross a certain threshold for the angle of the angle of the mountain, then it will collapse, right? And then it builds itself again. So it drives itself all the time to this stage that it is collapsing. It's a little bit masochistic, right? So it all the time drives itself into the critical state. That's why it's called self-organized criticality. So, and you can model this also with the computer. It is something that is slowly driven. It explains non-equilibrium steady state, or that has an equilibrium, non-equilibrium steady state. And if you measure the avalanches, why I'm telling you all of this self-organized criticality stuff? I'm telling you this because what you observe in this model is something very similar what we previously observed for the sleep, right? So if you look at the avalanches of that go down this mountain, then you plot them on a double logarithmic plot, you get a power law. Okay, so the avalanches of this model follow a power law, whereas the times between avalanches, okay, this would be our sleep stages, sleep durations, they follow an exponential distribution. So you have the same kind of statistics here that you have for sleep. So you can say, oh, maybe I can use this framework, maybe I can use self-organized criticality to learn something about sleep. Okay, so here I wrote again, power law statistics for the avalanches, waiting times for the waiting times between the avalanches are exponential distributed, and Per Bak, a physicist from the Netherlands, he called it around the year 2000, he called it self-organized criticality. So the question is, can we use this model to learn something about sleep dynamics? Just a short side note. Per Bak, these were all theoretical physicists. So they never went to the beach and checked their theory by themselves, right? So because it turns out when you do this experiment in the lab, you find that for sand, you don't get this self-organized criticality behavior. You only get it for rice, for ores, okay? But then only when ores looks like bismati, when it is a bismati rice, okay, you need this elongated shape, otherwise you won't get self-organized criticality. So this is just a side note about how sometimes theoreticians come up with a framework, but then when you test it in the lab, it doesn't work out so well, okay, experimentally. But still, the framework of self-organized criticality applies to many things in physics. Good. So just another side note, this power law and exponential behavior you observe also when you go to study little baby rats. Okay, so what you see here is the statistics of baby rats after 2 days, when they are just 2 days old, and here when they are 21 days old, so 3 weeks old. And what you see is that for the sleep durations, you all the time have this exponential process, right? You all the time have a straight line. Why here the slope is much deeper than the slope here? Somebody can tell me this?
Because they're older?
Because, yeah, when they are 2 days old, their brain is very tiny, right? So that's why the slope here is much deeper. This is the same as what we saw here. Tiny brains, big slope, okay? Bigger brains, less steep slope. So this is the same as what you see here. When they get bigger, their slope gets less steep. However, when you look at wake, in the beginning, you don't have a power law. You don't have a straight line, right? You don't have a straight line. Only when they get older, you develop this power law. So seems to be something related to the developing brain, okay? This behavior. Good. So the question is, how can we model this? Can we come up with a simple model that includes a bit of sleep physiology, namely a network of sleep and wake promoting neurons to reproduce this arousal and sleep dynamics, okay? So now you open a book or a paper on sleep regulation, and it's very complicated. So you see here what happens when you are awake, okay? You have here all these centers in the brain. This is the brain stem here. Here's the thalamus, the hypothalamus, and you have many different neuronal centers that are responsible for making you awake, okay? So some, like the basal forebrain, they are more active when you're really focusing on something, to learn something, whereas LC, locus coeruleus, is firing basically all the time, okay, during wakefulness. So all of these different clusters here, they make you awake, and they project to the cortex to keep you awake. Whereas when you go to sleep, then all these centers here, all these centers, they have to be silenced. And they are silenced by a neuronal center of sleep-promoting neurons called VLPO, ventrolateral preoptic area. So this is kind of suppressing these centers, okay? It's pushing the activity down that you keep asleep, okay? Good. So in physics, we need to simplify, okay? Otherwise, we are lost. So we cannot explain nothing if we take all the variables and parameters into account. So we need to simplify. First thing to simplify is, we are just looking at sleep, okay? We are looking at the sleep process. We are not interested what happens during wake, at least not for now. So we exclude this. So we already reduced the problem to 50%. And now we focus on what's going on here. And we just say, okay, instead of having all these different wake promoting centers, we say all of this, we just say is one network of wake promoting neurons, and the VLPO is a network of sleep promoting neurons, okay? Good. Next, we look a little bit at literature on people who did experiments on coupled networks of neurons, and we find something that's very interesting, namely that when these wake-promoting neurons, okay, all these wake-promoting neurons, when they are suppressed, inhibited by VLPO, by this sleep-promoting center, they still have an intrinsic neuronal noise, okay? They are still wobbling in activity. They cannot fire because they are suppressed, but they are still having some underground activity, so to say, because they still have ion channels that open and close. So all of this you can say is neuronal noise. We can call neuronal noise. And so neuronal noise, it's correctly, it's called subthreshold voltage fluctuations. It doesn't cross the threshold. That's why it's subthreshold. And there are also two main sources, perhaps not so interesting at the moment. But what is interesting is that this neuronal noise is temperature dependent. And very interestingly, temperature dependent in a way that is counterintuitive to us. Because usually what happens in physics, when we increase the temperature, usually noise increases, right? We have more noise when a system is more at a higher temperature, so to say. So here, it's not the case. You see that temperature increases and neuronal noise. So this is just a measure of the neuronal noise. It's a standard deviation of some signal. So this neuronal noise decreases with temperature. Okay, so these are different kind of neurons here. Don't worry about them. But so the opposite happens of what we are familiar with in physics. When you decrease the temperature, the neuronal noise increases. This is something very important and very interesting for our modeling that we need to take into account. And now we are ready. We have all the ingredients to make our model. Okay, so we said we make a network of wake-promoting neurons. Okay, we have here wake-promoting neurons. Each of these wake-promoting neurons has a particular noise. Okay, this is shown here, different noises. So you have N neurons and you couple them together. Okay, you couple them together like in electrostatics. You couple together circuits, and now you integrate this current. And what you see is something very interesting. So if you take all these noises together, from time to time, you can get a superposition of these noises that cross the threshold. Okay, that cross the threshold for activating a neuron. So you cross the threshold, and when you cross the threshold, you fire to the cortex. You fire to the cortex, you get an arousal, but at the same time, you have your VLPO, right? You have your center that wants you to go back to sleep. So you activate at the same time your sleep promoting neurons, and they lead to inhibition to get everything down, okay? To get the activity down that you go back to sleep. So this is what this simple model tells you. You have all the time this integration. Sometimes you reach the threshold, you fire to the cortex, you have a short awakening. At the same time, your sleep promoting neurons get more active, lower you down, okay? And you go back to sleep. Good. So you can also write this in some equations. You can say, okay, if I just look at the overall activity, maybe first we look at this upper plot, then we look on the equations. So you look at the overall activity of these wake-promoting neurons, and you put here a threshold at 0 when they are firing, okay? When they are firing to the cortex, you say this is 0. So when you are above 0, you are awake. When you are below 0, you are asleep. Good. When you are asleep, you cannot go deeper than the deepest sleep. Okay. So therefore, you need to have here a boundary. Okay. You see here the boundary, this deepest sleep you can get. And when you are above 0, then you have something that brings you back to sleep. So you have a sleep restoring current. Okay. So you have here you see these sleep promoting neurons, they have this inhibitory current that puts you back to sleep. So now you have this kind of trajectory. You can model this simply with a random walk. Okay, you can just throw a coin. Okay, you throw a coin at every time instance, and you say, when I'm +1, I go up. When I have a coin, I have one side and the other side. So if I have the one side, I go up. When I have the other side, I go down. And this way you perform a random walk. If you are below 0, your random walk is completely free. Okay. The only condition is that when you reach to the lowest, to the bottom, you cannot go lower, and you would, if you now throw again a number that would let you go down, you keep down. Okay, so you cannot go lower than this. But when you are above 0, then you have here also this kind of force that puts you down. Okay, so this you have to take into account. So when you write this as equations, you see during sleep, it's completely free. Okay, it's a completely free random walk. Only condition is that you cannot go lower than the lowest, the deepest sleep. Whereas here, when you go to arousals, you have the same term. You see, you have this sigma d omega. But now you have this sleep restoring current. Okay, this is this term here before. So you can write it like this. So this is how you can put this now in your model, and you run it, and you run it for different temperatures. So how do you put the temperatures inside? You put it inside with this sigma. You remember there was this sigma here. So sigma is temperature dependent. So if you put a lower temperature, you would put a high sigma. If you put a high temperature, you would put a low sigma, right? And this is exactly what you do. You run your experiment, your computer simulation for a low temperature with high sigma, and you run it for high temperature with low sigma. And what do you see? You see that, I mean, what do you see? Something interesting on this slide. Asking again. Any observation? Somebody wants to speak to me or not?
I think it's hard for us to understand at this point of our degree about some of the questions. But
yeah, but you are, I mean, just when you look at the figures, what do you see? We said everything below the dashed line is sleep, everything above the dashed line is wake. So what do you see for low temperatures? What do you see for high temperatures? Just looking at this.
that the voltage is higher when you have low temperatures.
When you have low, yeah, you have basically more awake, right? You see, it's more awake. Actually, it's shown here. When you are at low temperatures, you have more awake, more arousals. When you're high temperatures, you have less. Okay, this is what you see. So if you plot now the time or the number of arousals versus temperature, okay, you can take particular temperatures, then you see more arousals for lower temperature. You see this? 34 degrees, less arousals, and 25 degrees more arousals. Okay, everybody sees this? Yeah, so this is what our model predicts, so to say. No, our model predicts more awake when we are at lower temperatures. Good. How can we test this? Experimentally, I mean, I can tell you a lot, but like this Per Bach, you know, who said self-organized criticality when you take a sand pile on the beach, and then Jens Feder, who tried this in the lab, he said, no. With sand, it doesn't work. You have to take rice, but not any rice. You have to take basmati rice. So, I mean, how can I I have this prediction. I say lower temperature, more arousals, higher temperature, less arousals. So, but this just comes out from a model. So how would I test this experimentally? Any idea?
You would test how aroused people in different temperatures.
Yes, but the problem is, Yuval, that we are mammals, right? So when I put you in the freezer, you don't cool down, at least not immediately. You know, you keep your temperature for a couple of for some time, right? It's not that you immediately go to minus 10 degrees, you know? So you keep your temperature. It's difficult to do this with humans, okay? You need something that, I mean, where you can manipulate the temperature and you get really the animal or the organism into this temperature, right? And do we know an animal where we can do this easily?
I think lizards or other cold-blooded animals.
Yes, so I told you in the beginning that we worked with Leo Appelbaum, who has zebrafish. So you just take fish. You take fish because fish, they behave differently than Yuval. Okay, Yuval you put in the freezer and he will keep his temperature, but you put a fish in the freezer. Okay, freezer is not good. Let's take a fridge, okay? So, and the fish, also the body temperature of the fish will eventually go to the temperature of the surrounding. Okay, so we went to Leo Appelbaum. As I told you, he has this lot of, in the Nano building, he has this aquarium with a lot of fish. And we told him, measure your fish, okay? We tell you that, so we showed him the blue curve and we told him, we predict that your fish are less awake when your water temperature is 34 degrees and they are more awake when they are in a water temperature of 25 degrees. He said, you're a crazy physicist. I don't believe it, but I do it anyway because I'm your friend. I do it anyway. It doesn't cost me a lot. I can just do this for 1 week. And he came back with his data and you see they match pretty well the model, right? I mean, looks like there is something in this theory that we just talked about with these two networks and how they are coupled. And you can repeat, I mean, you can do this, you can also measure the percentage of sleep. Blue is always the model and red is the experiments. So they also pretty well coincide, and this we already saw. And you can also take the mean sleep bout durations and the mean wake bout durations. So it looks like it's agrees very well with the model. And since this model, I forgot to say, actually this model with the random walk was very much influenced by ideas of self-organized criticality, because you get exactly this statistics from this model, as we discussed before with the sand pile, power law behavior for the awakenings and exponential behavior for the sleep states. So you can do also the statistics for this, and you see that here for wake, double logarithmic plot, okay, double logarithmic plot, you see straight lines for the experiments, for the model anyway, because the model is based on the self-organized criticality framework, but also for sleep. You see sleep here, logarithmic and linear, straight line, and you get this for the experiments as well as for the model. So looks like we found some reasonable model to explain these short awakenings during sleep, at least in fish, okay? At least in fish. So just to summarize briefly, brief arousals, as we learned, are integral part of healthy sleep regulation. We find them all the time. We find them in young people. You have 10 to 15 awakenings, short awakenings throughout the night that you're not aware of. And we found them in mammalian species, so in people, but also in cats, rats, and mice, but also non-mammalian species. So we also find this actually for zebrafish. I didn't talk about this, but there are a lot of papers also discussing this. These arousal durations, they show a power law distribution, which is scale invariant. So it doesn't make sense to talk about a typical time scale or time duration for wake, for arousals. And the sleep stage duration show an exponential distribution. So they have a specific scale. Okay, there is a, as you remember, we found 22 minutes average sleep duration for humans. We can explain this kind of behavior with by this neuronal noise fluctuations in wake-promoting neurons that might be the origin of this spontaneous brief arousals during sleep. And arousal statistics changes with temperature, okay, because this neuronal noise is dependent on temperature. So if more arousals is lower temperature, and at least for ectothermic animals. So ectothermic animals are fish and also crocodiles, you know, that or snakes that change their body temperature according to the environment. So the question is, why is this important? I mean, okay, so we explained something for zebrafish, okay, but why do we care at all? You're laughing now, but I'm telling you, he's coming back. Okay, so so we thought we got rid of him, but he is coming back. So so why it is important? It is important for several reasons. So one reason I was particularly interested in is sudden infant death syndrome. I think
someone wrote that in the chat, I think, about Daniel.
About whom?
He wrote that there was a study on zebrafish that said that high temperatures are responsible for the crib death in infants.
Yeah. This was our paper, I think. Or if he finds another paper, then he should send me, because I haven't seen anything that followed up on this. But I would be very interested to see this. So just to give you quickly the story. So sudden infant death syndrome, I think it's called in Hebrew Mavet Ba'arisa. Ba'arisa. So this is something very, okay, thanks. So this is something very, very bad, okay? So I mean, we don't need to talk about how bad it is. I just want to tell you that people don't know why this happens. Okay, people don't know why this happens, and but there are recommendations. Okay, based on experience of many years, there are recommendations to the parents. So one of these recommendations is to put the babies on their back. Okay, when they go to sleep, you put them on their back, not on their belly. Another recommendation is don't put them too many blankets, okay? And keep the temperature in the room lower, okay? Keep the temperature in the room lower. And there are some other, there are also other recommendations, but these are the most important ones. And but you see, they're all related to temperature, right? They are related to temperature. Don't put too many blankets. So to put the baby in too high temperature. Don't put the room temperature too high, also related to temperature. When the baby is sleeping on their belly, it also preserves more temperature than when you are laying on your back. Okay, when you go for camping and it's very cold outside, you go to the midbar for camping and it's very cold in the night. How would you sleep in your sleeping bag? Are you sleeping on your back or are you sleeping on your belly and put your hands in? Question to you. I mean, what are you doing?
Yeah, on our belly.
On your stomach.
On the stomach, right? I sleep on the stomach like this to preserve temperature. Because when you're in the summer, you try to sleep on the back, you know that you don't accumulate temperature. So everything is related to temperature, but no explanation. Perhaps we find an explanation for this with our model. Let's see. First of all, when you take a statistics of how many babies die from sudden infant death syndrome, it's called SIDS, then you see it's very much dependent on age. Okay, so here's the month. So you have the most is between 2 and 3 months of age. Okay, 2 and 3 months of age is also very critical for the baby because it has a change of thermoregulation. Okay, you see here thermoregulation versus age. So at the age of 2 to 3 months, it is most vulnerable. So the baby is not able yet to control its own body temperature. Okay, before it didn't have to do it because it was inside the mama. Okay, it didn't need to control their temperature. Now it comes outside, so it takes time until it can control their body temperature. So basically, when you look at the first month of age, you can say the baby is like a fish. Okay, the baby is like a fish, very sensitive to the external temperatures. So thermoregulation in very young infants is not fully developed, so they show behavior like fish. So they are more susceptible to higher ambient temperature. So when you put higher temperature, okay, when you put higher temperature, then the baby also receives this higher temperature. Also the body temperature of the baby is increasing. So how is this related to sleep now? It's related in that way that if you have a baby that already has low levels of neuronal noise, okay? Low levels of neuronal noise, and you put it in a high temperature, then you even make it less susceptible, okay? Less susceptible to environmental changes. So if you if you put the baby in a too high temperature, okay, then it sleeps very well. It's good for the parents. Okay, the parents can sleep also better. But if the baby now gets into a situation, for example, it's stuck with their mouth somewhere and it cannot turn the head, then it won't wake up. Okay, it won't wake up because it's just sleeping too deeply. Okay, it has a low neuronal noise. Lets the baby not wake up. Has a low arousability, and then it can stop breathing, so to say. Can stop breathing, and this leads to a fatal outcome. Whereas when you put the baby in a cooler environment, okay, you have a higher neuronal noise. The baby may wake up more often. Okay, not as good for the parents, but more protecting for the child, okay, because it can wakes up and it can start to breathe again or to start crying, and then somebody comes to help him or her, and that's the kind of potential impact of the model and the research we talked about. Has to be shown experimentally, but it's very difficult to convince parents to give up on their baby and to let it put into a high temperature environment. Okay, so I don't know how to test this experimentally. Good, so that's basically it. Thank you very much. Toda rabba. If you have any questions, I'm happy to answer and discuss.
I have 2 questions actually.
Yes.
One of them was in the other graph you showed that showed how babies control their temperature. It starts like high and then it goes down at the age of 2 months and then it goes up again.
One moment. Here, you mean you talk about this?
No, this one, yeah.
Yes. So you see that this is a thermoregulation, right? So this point, this is not really higher here. This is not significantly different. So you can say that in this time they are not there's no difference basically.
No difference. Okay.
No difference. They are basically, they start at a low level and just over time they increase. You have a little bit maybe you know, when actually it's not quite true. When they are born, babies have more fat. You know, they have more brown fat, so they can keep better their temperature in the very beginning. But then at age 1 month, you know, the fat reserves they disappear, and then it needs to switch to an active kind of thermoregulation. Yeah, to a different mechanism. So they have a little bit advantage at age 1. You're right, but not much. Okay.
And the other question was, I wanted to ask if you said that temperatures doesn't affect adult mammals, and like they don't affect their sleep. And I wanted to ask if it has anything to do with that we are hot, like we sit in our home and the AC is on heat, we get sleepy. And if I want to ask if it got anything to do with it or
yes.
something else.
No, when you do the statistics, you do the statistics for here. You do the statistics for people, and this is the outside temperature. Okay, so 25 to 34. You see the same, a very similar behavior, but we don't have an explanation for this because it's not. You also see that when you are in a hot environment, you have less arousals. Doesn't mean that you sleep better, but you have less arousals during the sleep. And when you are in a colder environment, you have more arousals. But for humans, the body temperature is constant. It's around 36 degrees. Doesn't change much if we are on 25 or on 34 degrees. So we cannot explain this. I don't know.
We don't
you
know.
You showed this. You see the same thing, but we don't know. We don't know yet because we cannot do the same simulation. You know, we cannot say during high temperature you have more arousals because during low temperature you have more arousals because the neuronal noise in your body is higher. We don't know. But very good question. So you can come to do a PhD with me and we can find an answer for this.
For 5 more years maybe.
5 more years. Okay, I'm happy to wait.
Thank you very much.
Yes, thanks. Well, any other questions?
Yeah, in the beginning of the lecture, you spoke about you had the graph with the levels of sleep, the deep sleep, the light sleep, and the REM sleep. And you said if people were to get less sleep, that throughout the night, then it's not good. And I wanted to ask if there have been studies of proof of long-term effects if someone's sleep cycle were to be like that over a long time.
You mean long-term effects of not getting enough sleep? Yeah, there's many. There's many because most people don't get enough sleep. So, I mean, there is one guy in the US, Plewise, big professor in, I don't remember, some in Pittsburgh. No, I don't remember, Baltimore maybe. He claims even that chronic sleep deprivation leads to Alzheimer. I mean, he bases this on animal studies on mice and rats, but I don't know. But what is proven is that if you are chronically sleep deprived, then you, I mean, somebody who is chronically sleep deprived runs into problems with metabolic disorder, meaning increase in body weight, body fat, but also higher levels of appetite and also cardiovascular problems. So people who are more sleep deprived, they down the road are more have a higher chance of getting problems, heart problems, and And also you can show that people who are sleep deprived, they don't learn as well, they don't perform as well. So there are many studies on this. They make more accidents. So there's a big study now in the US that shows that doctors who are on 24-hour shifts or longer hour shifts, they have a higher risk for making accidents, road accidents. So it's very serious. They are now fighting to let the doctors sleep, work less hours, you know. And doctors and nurses the same.
Yeah. And have there been proof of like long-term effects on the level of illnesses on the brain?
Long-term effects of sleep deprivation on illness of the brain. I don't know if directly. I mean, there are proofs for these levels on the heart, but on the brain, I mean, it's difficult to tease out what is the chicken and the egg, because if you have heart problems or problems with your or cardiovascular problems, and you don't get enough oxygen to the brain, then you would damage the brain because of a cardiovascular issue, and you can get also a stroke because of a cardiovascular issue. But I don't know if this was teased out, you know, whether direct influence on the brain because of sleep deprivation, or indirect because you won't get enough oxygen to the brain, and your arteries, they get more stiff, you know. So I don't know. I'm not a medical person. I can't tell you. But what I can tell you is that there were experiments in the 70s or 80s of pushing people to stay awake, not to go to sleep. And I think the record, I have to look it up, I think it was 20 days or something. I mean, very long, quite a long time, where this person was a student of psychology. He was not allowed to go to sleep, and he became very aggressive, you know. So he needed to be under constant observation, and somebody needed, because he all the time wanted to sleep, you know. He had such a strong sleep drive that you talk to him and he fell asleep. So you had to have somebody who is punching him that he wakes up. So there was this direct relation between sleep deprivation and performance and hallucinations and psychological disorders at the level of sleep deprivation. But after they finished this experiment, after 20 days or so, I have to look it up, he went to sleep, and he needed 14 hours of recovery sleep, and then he was okay. You know, there was no damage. So nobody died yet of chronic sleep deprivation, at least no humans. For animals, you can show when you put mice or rats in an experimental setup, very cruel setup. It's like you put them in a kind of a small swimming pool on a boat, and if they would fall asleep, they would fall into the water, you know, and then they need to wake up to swim to get back on this little boat. And this way you can sleep deprive, avoid mice and rats from going to sleep. And there they could show that, that they killed this way mice and rats. Okay, they were just so by not sleeping they would die. But this hasn't happened to humans. I don't think anyone would agree to participate in such experiment also.
Yeah, you're probably right. Okay, thank you.
Good. Okay. Thank you so much, and have a good rest of the week, and Shabbat Shalom.
Thank you very much.
Thank
Thank
you.
you.
Bye bye. Toda. Bye.